Hi, and welcome to Unit 11, Simple Regression. And I want to make sure I'm sharing my screen. There we go. So I have pulled up the lab notes, and I want to go over just a few things about regression. So what does a regression measure? And it's used for prediction. So one of the key things that we want to do here is, unlike correlation, which is two DVs, we're changing from two DVs to not quite an IV and a DV because an IV is manipulated most of the time. But we're changing to something called a predictor. And what this simply means is it's occurring in time before the dependent variable, or in regression, we call it a criterion. So we're switching to from IV DV language to predictor criterion language. And a classic example in IO is your predictor is a selection test and your criterion is the performance appraisal score. And so the significance test evaluates whether the X or the predictor is useful in predicting Y, or the criterion, or how well it does. And so here we've got a model and we're measuring. Some examples would be predicting total monthly sales from the amount of overtime that that employees work. Predicting leadership effectiveness from a score on an introvert or extrovert assessment, personality test, or validating a selection system by using interview and personality inventory scores to predict performance. And so, what are the assumptions of a fixed effects model regression? And it's the dependent variable is normally distributed in the population for each level of the independent variable, and that the population variances of the dependent variable are the same for all levels. And the cases represent a random sample. And then we have a lot of the assumptions from correlation. It's linear. We don't have range restriction, and those that we covered last week. And so what's the difference between a fixed effect and a random effect model? And a fixed effect model assumes the relationship is linear, and a random effect could be squares, cubes, or other things. And just like we did for correlation, we look to a scatter plot to check the linearity of the relationship between X and Y to make sure it is linear. And so I want to go over the regression equation, and I'm going to draw it up here. Okay. So it's drawn a couple of different ways. Right here we have, this is called the predicted Y. This is the dependent or criterion. This B with the 0 is the constant. This B with a 1 is the beta weight. And this X1 is the score of our independent variable. It can also be written the other way. But I just want to point out, this is the, when we're looking at the line, the Y is this point right here. I'm actually going to use a different color so you can see where it hits on the Y. It's called the Y-intercept. It's right there. It's where the line comes in on the Y-axis. And this really is telling us, what do we know about our independent variable, or I'm sorry, our dependent variable with no other information. So we call this the Y-intercept. It's my abbreviation. This is the constant. All right, this is the beta weight. And this beta weight, I'm sorry, I just totally screwed up. I'm sorry. The BO is the constant, the y-intercept. This is the or this, I'm so sorry, this is the dependent variable. Oops, we get out of the, this is the dV. I'm sorry, this constant is basically the mean of the dependent variable. It's what we know, and that's the y-intercept and where it enters in the line. This is the beta weight, and this is the IV, or the predictor, and it's the score. Okay, so this equation forms the line, and this beta weight is also referred to as the slope. And what that means is this B1 is a weight, and it tells us the unique contribution of this variable. Now, right now we only have one variable, but next week we'll have multiple variables. And so it's a partial correlation that's telling us the unique contribution of this variable. How important is this to the line? And another way to think about it is for each unit in that you move over in X, how steep do you go up to Y, right? So it's kind of, you can think of it like a ladder or a step. So this is telling the line how steep to be. So if this variable doesn't have a lot of influence, your line's going to be rather flat. And if it has a lot of influence, it's going to make a steeper line. So what is so cool about regression is that we can use it to predict the future. So if I run a correlation, I'm sorry, a validation study. Sorry, I shut the window, it got loud outside. If we run a study, and let's say I gave you all a some type of selection test, and I wait till your first semester through, and then I collect your GPA. So this would be the GPA, and this would be the test. Let's say I give you a critical thinking test. So I would run the regression on your group of students, and it would give me numbers here, right? And so it would fill out these numbers. And then what I could do is next fall, when someone comes in and takes the test, I could plug their test score in right here and solve and say they're most likely going to have a GPA of whatever this equation works out to be. So it helps us be able to predict things in the future. Furthermore, if I'm like, I only want to hire people, or not hire people, but select students that are going to have a GPA of 3.0 or higher, I could put in 3.0 here, and with the numbers I got from when I first ran it, I could solve and find out what test score or what cut score I should use when, you know, what score do I cut off and not accept when giving this in the future. So this is a very powerful tool for IO psychologists. Okay, now some things to understand. Just like ANOVA, we have a model, we have model stats, and then we have individual predictors. So in ANOVA, we had the F test, which said, hey, this is significant. And then we had post hoc tests, which said, okay, here's where it is. And in regression, we have the R square, which is the proportion of variance. that the entire model counts for. Now, right now we only have one independent variable, but next week we'll have more. So if this is 0.25, then that means that X accounts for 25% of the variance of Y. So very easy to explain. Now this is the model. So this says, hey, is this model even, this whole line, is it even worth looking at? And if it's significant, now it's, you know, there's an F test and a P test to tell you whether this R squared is significant. Then if it is, then you look at individual beta weights, right? Right now we only have one, but you have a little b, which is unstandardized, and you have a big B, which is standardized. And I'll show this to you in just a minute. But this is in the metric of this. So if this test was 1 to 100, it's going to be a weight that's appropriate to weight that score. But we standardize it, or SPSS will standardize it for us. And this acts more, it looks like more like a correlation coefficient, and I can use it to compare multiple variables. So these are the important statistics you need to know. Now, on this B, you know, which will be one line, you'll have a T and a P telling you whether it's significant, and confidence intervals for future beta weights. So these are the stats that we need to pay attention to. Okay, so let's do our first activity. So you have a boss that believes employee performance is determined by their conscientiousness. And once you get to personnel, you'll learn this is one of our biggest predictors. She wants you to run the numbers to identify any significant relationship between conscientiousness and performance. And you're going to use this data set, and we're going to look at this conscientiousness. So I have it up here. Let me clear my drawings. All right. So, and stop drawing. Okay. So here you can see we've got conscientiousness. Let's look. Conscientiousness, these are the big five, and then overall performance, that's going to be my DV. So we're going to follow the steps right here. Go analyze, regression, linear. We're going to move the criterion variable or the dependent variable, this overall performance, to dependent. We're going to move conscientiousness to independent. And then under statistics, we're going to check, estimates is already checked. We want confidence intervals. Model fit is checked. Descriptives. We don't need part and partial correlations here because we only have one, but we will in the future. And hit continue and okay. Now, here is our output. So first it gives us the mean and the standard deviation. It's also going to give us a correlation matrix, which here they're going to be, it's going to be the same. This correlation is going to be the same as the multiple R right here. And the standardized coefficient, because there's only one variable. But this will be very useful, as I went over last week, in seeing how it changes from the initial correlation to a beta weight in the model. Okay, this box is just telling you what variable you have, what method you use. We're always going to use enter. Now, what we care about here is this R squared, because this tells us our model, right? And so we care about this. This adjusted R squared tells us what we'd be likely to get in another sample. And then we're going to read this line right here. 1F, this is our F test, telling us the significance of this, right? And then we're going to need to report the degrees of freedom of error. Now, so I also just want to insert a title and write this up. Oops, not there. This back to where it was. There we go. Okay. So in order to write this up, we would say, the model of conscientiousness predicting performance was significant. R square equals, now you're going to want to write this the correct way, italicized with the two superscripted. Oh, I'm sorry, it's not, yeah, it's 0.025, which we're going to round up to 0.03. And then our F is, our degrees of freedom is 1 to 65, and our F equals 6.91. And our P is less than 0.05. Okay. And so hopefully you can see where I got this from. So the other thing we would write is, this model, which right now only includes one variable, but when it includes more, it wouldn't be multiple variables. This model accounts for 3% of the variance of performance, which doesn't seem like much. But is significant, and we'll show later what that looks like. Okay, so I'm going to clear the drawing. And scoot this up. And yeah, so let's look at the conscientiousness. So here, this is our unstandardized beta weight. And we would write this as B equals 0.003. Typically, we wouldn't go 3 decimal points, but this is what this is. Now, our standardized beta weight is, and this should have a little tail, equals 0.16, rounding up. Okay, and so if I were to write this, oops, let me do it down here. Okay, so we'd say the individual predictor of conscientiousness was a significant, or I should just say was significant. So I've already said predictor. I don't want to repeat the same word in the sentence. Comma. Now you can report either one. I'm going to go on and report the big B, 0.16. My T, now my T value is right here, this 2.63, but my degrees of freedom is going to be this residual number up here. So I'm just going to jump back up here and grab it, 265. And my T value is 2.63. And my P value is, P is less than 0.05. And you can also see our confidence interval. If we were to run this study again in the same organization, we could expect the beta weight to be between 0.001 and 0.005. Okay, now the last thing that we need to do is graph this. And you'll see over here, I think you guys should be pros at this by now, but we'll do go through this. Graph, legacy, scatter dot, simple scatter. And then we're just going to take conscientiousness on the x-axis, overall performance on the y-axis. Here it does matter. And hit OK. Let me clear my drawings. Okay. So good. We look here and we see there's no U-shaped pattern or S-shaped pattern. I do notice this does not look good and we would want to change that. I'm going to find this fit line at total just like we did last time. And you can see the line's not very steep, right? So what this tells me is I would want some other predictors in here. It's telling me something, but it may not be as critical for this job. So I might look for another test, but it is significant and it would help us. Right. And so the last thing that I want to show you is how to write out this equation. And so let me do it up here in this. So this is something you haven't done before that you're going to do with all your regressions. You're going to write the regression equation is overall performance equals. So I'm just substituting in the words for what we just looked at. Equals, now I need to put in my constant. So this is my B sub 0 right here, this 3.124. Now, in the equation, you must write out to 3 decimal points because the equation won't work if you don't. So, and it's going to be a plus sign because this is positive. 0.003, this is my, so this is my DV. This is my B0, this is my B1, and in parentheses, I'm going to put conscientiousness, right? So what's really cool is I could plug in a conscientiousness score and see what the performance would be and set a cut score. So those are all the things that you will need to run a regression and be able to report it as simple regression. And next week we will do multiple regression with more than one variable. I hope this was helpful.